Hi, my name is Julia Silly, and I'm a data scientist and software engineer at our studio. And in this screencast, we're going to use this week's Tidy Tuesday dataset about Canadian wind turbines. And we're going to build a model to predict the capacity, the energy generated by the wind turbines from other characteristics about the wind turbines, like how big they are and when they were commissioned. So we're going to use a decision tree model, which decision trees are really nice kinds of models that you can understand. Like, they're very interpretable. They have a lot of nice characteristics, and we can understand a lot about them after we have the model trained using variable importance and visualization. Let's get started.
All right, let's learn about these Canadian wind turbines. So this is this week's Tidy Tuesday dataset, and we can load up the data here. So this is a data set of wind turbines around Canada, and we can see we have a lot of different information about them, including where they are, how big they are physically. There's measurements about the rotor diameter and the hub height, and then the model information. And then we have this variable contains the capacity, like how much energy they generate. So in this screencast, what we're going to do is we're going to build a model to predict the capacity of these turbines based on the other turbine characteristics. So there is, I saw there's a really great blog post by another tidymodels person, Simon Couch, where he used this same data set as a way to learn about stacks, the newer tidymodels package for how to do ensembling, like model stacking and ensembling. So you should definitely check that out. I'm going to take a more straightforward approach here and just train, just one kind of model, but we're gonna tune and so fit and tune a decision tree model and talk about how to do regression with decision trees and how to interpret them. So before we do that, let's do a little bit more data preparation. So there's a couple of things that I noticed about this data that we have. So first off, we have the year that the turbines were commissioned, but notice that it's a character instead of a number, and that is because some of them are like 2014, 2015. So some of them are actually years, but then sometimes they have something more like a group of 2 years. So we would like to use this as a numeric variable, not as a character variable. So we're going to use a function. So first let's set up some of our new variables that we want to use. So let's take that commissioning date, and let's use a function called parse number to get out the commissioning date here. So when we do this, what happens is it basically looks for the first number it can find. So what happened, notice before we had this many 2014s, and now we have this many, because for all of these, it called it now 2014. So they all go now into this bucket. So that's going to be good enough for our modeling purposes here. We are going to convert everything that was of this form. It will go in there, and it'll find the first number here. Parse number is a really useful function that I find myself using a lot in situations like that. So what else do we want here to do a little bit of data preparation? Let's see what we've got here. Let's say names like this. So the thing we're going to predict, our outcome, the thing we're training a model to do, is this capacity. So that's kind of long. So let's say turbine capacity like that. And then let us get definitely the things that are about how big it is, like the hub height and the rotor diameter. And so that's some numeric variables. And then there are also some categorical variables in here, like the province, where it is located. We also have latitude and longitude, but let's just use a categorical variable for location here. And the model. So there are a whole bunch of models. Model of a different sort than what we're training, a different use of the word. So these are like, you know, model numbers for turbines, things made by GE or other kinds of manufacturers of wind turbines, but there's 92 of them, which is too many here. So what we're going to do is we're going to use a function called fact lump n, which is going to lump together less frequently occurring levels. Let's say we want to keep the top 10 and make everything else will turn into other. And you know what? Let's do the same thing for province or territory, because oops, that's not what I meant to do. Province, territory, because some of these are very, very seldom used. In fact, let's do, I don't know, let's do like 8 or something, because some of those are very infrequently occurring. Let's just keep like the top 8 or something like that. The other thing I think to notice, we are predicting this turbine capacity, but for a handful of the observations in our data, we do not actually have any measurement of the amount of energy it can predict, or it can generate. So we are going to need to filter those out because we don't have anything to you know, to put in there. And that looks good. So while we're here, let's convert the things that are characters to factors, because we're going to be using this for modeling where factors make more sense. Like so. All right. So how much data do we have? All right, not bad, not bad. Let's make one exploratory plot before we get started on our model. Let's look at those numeric variables. So if we take our data frame here and let's select the turbine capacity through the oh, why do they have, did I do something weird? Transmute turbines. Oh no, that's good. Okay, so turbine capacity through commissioning date, like so. So let's select these, and then we are going to pivot longer. Oh goodness, there we go, pivot longer. And we are going to pivot everything but, so we're going to take rotor, the rotor diameter through to the to the commissioning date, like this. All right. Wait, something is slightly strange. Why does it have all these extra things? Turbine. Oh, I put the whole thing back in there. That's not right. I'm like, wait a minute, what's going on here? Turbine capacity is equal to, I put the whole data frame. Whoopsie, we don't want that. We want it to be turbine rated capacity there. I put the whole little data frame in there. That's kind of strange. I'm like, wait a minute, why does this look so strange? There, that's what we want. That makes a lot more sense. Okay. And now we can reshape this so that's a long skinny data frame and then pipe this into a plot. So let's put that capacity on the x-axis, value on the y-axis, and let's put some points on there. I bet we're going to make them transparent because they're going to be difficult to see. And let's facet wrap by that name there. And I bet we'll need to do scales equals free y, like so. Okay. Okay, so this is how are these numeric values related to the turbine capacity? So the rotor diameter, the hub height, and the commissioning date when this wind turbine was commissioned. So we've got some relationships that we can see here. It's really overplotted though. Like there's like tons and tons of wind turbines that are just plotted right on top of each other. Let's do a couple things. So let's put a smoother on top, and let's take away that y-axis. So let's make something that looks like this. Oh, that's way too curvy. Let's just put straight lines like this. So let's just make straight lines. And so that is looking better, but we still have this dramatic overplotting problem. So instead of a geom points, let's say geom hex, and what this will do, will make little areas and count up how many wind turbines are in these areas. I think they're a little too small, so let's make a few smaller bins. This is the bins in either direction. This looks pretty good. I think that looks about right. And the way that if you want to change the colors of this, you can say scale, fill, and this is a gradient. So for example, you can change the high color to something like cyan 3 or something like that. I think that's a nice darker one, which looks pretty good. So that looks pretty good. So let's make the aspect ratio of this look decent. Okay, so I think this is a good way to plot this kind of data when you have so much that gets overplotted right exactly on top of it. So what we can see here is so we've got these really bright hexes where we have many turbines that fall right inside of that hex. But we can see this, the relationship that the bigger the rotor diameter is, the more capacity the turbine has, and the same with hub height. And then we also see this relationship with commissioning date, that as time has passed, we see this, this general relationship that the turbine capacity is increasing with time, that turbines that have been commissioned more recently in general have higher capacity. So this is the kind of information that we want to use in our modeling. So I think it's time. Let's do it. Let's build a model. So let's start by loading the tidymodels meta package. And then let's start by getting our data sets already that we're going to need for modeling. So we start by making our initial split. So we're going to put in the data set we're using for modeling, and we can stratify by the turbine capacity like this. So this is we're not stratifying by a categorical variable. We're doing it by a continuous, but we can call that wind split. So what it's going to divide them up by the data up by quantiles, and then do stratified resampling within each of the quantiles. And once we have that split, we can make a training set, and we can make a testing set like so from the split. And while we're here, let's make some resamples, because we're going to use that for tuning our model. So let's call it wind folds, and let's make some v-fold cross-validation. And so what we do is we will make cross-validation folds of the of the training set, and we can again do stratified resampling and put in the turbine capacity as the thing we will use for resampling. So let's run all that. V-fold CV, sorry. So let's run all that. So now we have, 10-fold cross-validation resamples. So in each of these, so if we look at like the wind split here, we have of the total number of things in the data set, all the data we have to start with, how many are in the training set, how many are in the testing set, and then of in each of the splits here, this is how many are in the analysis set, this is how many are in the assessment set for each of the resamples that we are going to be dealing with. So now it is time for us to get going on our modeling. So in this example, I'm excited to get to show how to use a decision tree, how to fit, tune, and evaluate a decision tree. So decision trees have a lot of really nice characteristics. They can be, pretty simple to interpret because you can really see exactly how it's making its decisions. You can really understand it through visualization in a lot of ways. So let's get started on that. I'm going to call our model specification tree spec. And so we're going to make a decision tree, and let's look at this. So a decision tree has three main tuning parameters. So the cost complexity, so this is like a cost for how complicated the tree will be. A tree depth, so how through how many nodes we can go down in the tree, and then min n, how many data points do you need to keep splitting your nodes. So we are going to tune all of these. So cost complexity tune, tree depth tune, and min n tune, like so. And then we are going to set the engine, set the engine to be, and the engine here is rpart, which is the excellent rpart package in R. And then the mode that we are going to use is regression. So we're going to be solving a regression problem here with this decision tree. So notice this is a tunable decision tree here. The next thing we need is a grid of possible parameters, or a set of possible parameters to try. We could use something like grid, like Latin, like one of these space filling parameter grids, like that are basically experimental designs to try to do the best job of trying different parameters to fill the space that you have, like a Latin hypercube design or maximum entropy. Here, I think let's do a regular grid. So a regular grid, instead, it takes a different approach and says, I'm going to try the same combinations of the same values, so that like every combination together. So we can use these helper functions from dials here, tree depth, that are going to help me set this up. So let's call this tree grid, like so. And so the default here is 3 values for each. So 3 values for the cost complexity, 3 values for the tree depth. And notice we're doing every combination of every value. We could, set something like levels equals 5, and that'll go, big difference right up. So this is how many models we're now trying, 125, so many. That would take a long time. I think maybe 4 would be good. Yeah, let's stick with that. That seems good. All right, so this is the model that we're going to try, and then this is the set of parameters at which we are going to try the model. So we don't know which one of those is going to be best, but we are going to try them all on our set of resamples data sets. So we're going to use tune grid. And I often, when I have done these screencasts, I've showed how to do this using a workflow where we put together a model and a preprocessor, and we stick them together and we carry them around in our code. Here, I am just gonna tune the model directly, and then the next thing I have to give it is a preprocessor like this. And I'm going to do this so that I can use the model in some RPart adjacent packages, and I can have access to the call and be able to use it more directly. So let's say the resamples I want to use are these folds that I made, and the grid I want to use is this tree grid. And then I'm going to let's set some metrics. It's always good to be able to remember how to set non-default metrics. So the defaults for a regression problem are RMSE and R squared, and then but we can also add other ones. Let's say we also are interested in mean absolute error and mean absolute percent error. I can add those in this like this. And so then let's call this tree result, like so. And let's set this going. So what we're doing here is we are, for each of these 64 possible sets of parameters, we are, for each set, so for 64 sets, we are training them on the 10 resamples. And for each of these resamples, let's go back to where we can see it, we're training them on this section of the resamples and then evaluating on this section of the resamples. So all 64 possible sets of parameters are getting trained on this, evaluated on this. All 64 possible sets of parameters are getting trained on this and evaluated on this. And so then we're going to have all those results and be able to use them to evaluate and say which of the 64 possible sets of parameters that we have are going to be the best for our situation. This definitely is going to take a while. I mean, decision trees are pretty fast to train. They're not super slow or anything, but this is going to take a while to get through all of those. So I am going to pause the video here and I will get started again when it's done. Okay, I'm back. It finished. So we have all these results, this set of tuning results, and now we can move on down here and explore our results and learn about them. So one of the first things we can do is we can collect the metrics and see what kind of results we have here. So this is for all of those, different results that we have. What are the results? So for the, this set of parameters, what are the results for the mean absolute error? What are the results for the mean absolute percent error, and so forth? It probably would be better to visualize this, because I am not good at reading a whole, table like that with my eyes. So let me try that again. So we can look at this. And yeah, I love theme minimal. I love theme minimal a lot, actually. But in a situation like this, when you have many little facets, small multiples, it may make more sense to use one of the themes that has boxes around it to be a little more clear. So what can we learn by looking at these results? So it looks like we want a small cost complexity parameter. We want deep trees. It does not like the stubby kind, and it, the metrics get better and better as we make the tree deeper and deeper. We also, it looks like, I don't know, we'll have to look at the metrics to be sure, but it looks like maybe it's getting better as we go to the smaller node size. So this is looking like this is looking like a complex tree. Like a complex tree is what is fitting this this data the best. A complex tree is going to be what we're going to be going for here. So we can keep going and learn a little more about this. So we can say something like show best for the tree result. And if we do like this, it will just pick a metric, but we can also say which metric we want. Like we can say, I want the best for this. And so notice it's the same, which is, you know, kind of good and helpful. So it looks like, you know, these really tiny values for the cost complexity, you know, 15, these really deep trees, min n of 2 or so. These are the things that are giving us the best tree. We can in fact say select best for the tree results, and you know, we can say something like RMSE like here, and so this will give us just one value. So this is the best performance here, and this gives us the config column gives us like some just information about which model it was that it picked. Something with, you know, we only had one preprocessor, it was the model or that formula, and then which model did it pick, which model option did it pick there. So this is what we want to use moving forward. And so what we can do is we can now finalize what we had there. I think before I've only ever shown how to use finalize workflow, but we can finalize a model as well. Here we finalize that tree specification that we have, and you know, we can put this in right here. We could save it and then use it, or we can just put it straight there, and let's call this the final tree. And look at it. So now this is not fit yet. This is a tree specification, but instead of having tune, now it has values there. So this is the this is no longer a tunable tree specification. This is now a tree specification that has values in there. So all of this work that we did up here to figure out what the values should be, we have now put it in there, and we have values at this point. So now we can, it's not fit yet though. It has not been fit to data. So we have a couple of different options for how to do this. We can just fit it. We can say fit the final tree, turbine capacity, and then we can put a formula in here, and we can say fit it to the training data. So we could call this, let's call this like final fit, like so. And this is a fitted decision tree. There's all the, you know, all the results. We also could use something called, let me just copy this and paste it. We could use something called Lastfit, which is like a convenience function that takes the tree, takes the preprocessor, and instead of taking the training data, it takes the split. And let's call this final result because it has a little bit more in it. So instead of just having a fitted model, which it does have in here, it has a workflow rather than just a bare model. So what Lastfit does is it fits to the training data like this does, and then it evaluates on the testing data. So these metrics are testing data, these predictions are testing data, this workflow is fit on the training data. So they're very analogous, but they are this one involves the testing data because it's giving you metrics and predictions on the training data. So both of these objects you can save. You could do something like save RDS for any of these objects, and then use that binary file later. Like if you've ever pickled a Python model or anything, it's the same idea. And then we can save it and then use it later to predict. So for example, if we predicted on final fit, we would send in some new data. So if we had, I don't know, this this, whoops, like this data here. But we also, we're pretending that is new data. We also can fit on this, predict on this. The part that we predict on is the workflow here, and it would be the same. And if we did, a different one, it's the same thing that's in both of these places that we would be predicting from. So you can, we're fitting, I don't know, let's see, let's call it fitting, let's call this predicting on new, predicting on new data. Now, so this would be like what you would do if in the future with it. Let's talk about, before we maybe did that and went off to have new data in the future, we want to understand our model a little bit more. So we can use, so trees have pretty, not overwhelmingly difficult to compute variable importance. So we can use the VIP package. So if we take that final fit, which you remember is a fitted tree, and we use the VIP function here, and we get a graph that looks like this. If you want to change how this graph looks, you can send in the aesthetics of like this: fill equals midnight blue, and you can say alpha equals 0.8, and you can also do things like scale y continuous expand equals to change, for example, this break, which I think looks nicer. So what is this telling us? It tells that the most important feature in predicting the capacity of these wind turbines is the rotor diameter. The second one is the commissioning date. The next one is the hub height, and then after that is the model, like what is the individual model of that wind turbine. So this is, it tells us what is driving the predictions. Decision trees. There's another really nice package that can be used for visualizing the output of decision trees. It visualizes the tree partitions, and it is really nice. I really like it. So the way this works is you take, the training data, and what you do is, let's see, let's put the most important thing on the x-axis, the second most important thing on the y-axis, and then let's put some points here. They are going to be overplotted, I bet, again. And then let's put the color here. So color equals turbine capacity. This is our outcome, remember? And yeah. So let's do this. So right now this is just points. Let's make that, let's do scale, color, viridis. And we are going to need to say aesthetics. So we're going to do color, which is what we already have, and then fill, which is what we're about to add. Here we go. Okay. So the thing we have predicted is this turbine capacity, and we have predicted it with these two quantities along with other things. And what Geom, these are all on top of each other. What if I did Geom jitter? Geom jitter, I don't know, let's try width equals 1, height equals 0.5. They kind of look like worms now, but at least you can kind of see where they are versus not having them all on top of each other. I think this is better. All right, so what we do here now is we put Geom part tree here, and we say, so it's going to go underneath, and we're going to make it really transparent, really super transparent, and we're going to say that we send it, the data is actually the fit. It is actually the fitted decision tree object. And then we say fill equals turbine capacity. The same thing that this thing has as turbine capacity, like so. Oh, I forgot about this. Tree can only have 1 or 2 predictors. So we have I don't know, five predictors or something like this. So what we're going to do is let's just make a little example fit. We're going to fit, let me just do this, fit. So this is for demonstration purposes. This visualization approach only works for 1 or 2 predictors like this. So this isn't exactly right because it's going to show us things for, this is going to show us things for a model that doesn't have the other predictors in it. So this is not our like final model that we're using, but it does give us a good idea. And I just love these visualizations. I think they are so clear and wonderful. And also they look like stained glass. They're so beautiful. Okay, so what is this doing? This is showing us the partitions where the tree, how the tree makes its, how it makes its predictions. So notice, and we have the color, you know, it moves from a low turbine capacity all the way up to really high turbine capacity over here. We notice that it's, you know, it's trying to make these smaller partitions where it's trying to catch, you know, these high capacity things versus these lower ones. It's trying to catch these in this section. So this is a really wonderful visualization approach to be able to use to understand this. We are missing a little bit here because we didn't tune this only with 2 predictors, whereas, you know, we're trying to look at this visualization here with only 2, but it still is we're able to like get a sense of what's going on in this, at least in this 2-dimensional part of the space. It would be really nice to be able to kind of do a higher dimensional visualization involving, you know, some of the categorical predictors and other things that we had in the full model, but this at least gives us an idea. Okay, we're almost to the end. Just the last thing we want to do is talk about the testing data, which we haven't talked about yet. So goodbye, beautiful graph. So let's collect the metrics for that final result that we have. So this is the RMSE for the testing data. This is the R-squared for the testing data. And then we can also collect the predictions out of that final result objects that we have. And we can make a quick plot where we put the true, for example, if I show you what we get from here, we have the true turbine capacity, the predicted turbine capacity. And if we put the true one on the x-axis, the predicted one on the y-axis, and then we make a few things like let's put a slope equals 1, dashed gray, transparent line. Let's put those points on. So then let's look at how our predictions did. All right, so you can still tell how much overplotting there is because of how many turbines had exactly the same capacity, but we have really good agreement for a lot of these, and there's just a couple that our model was not able to predict correctly. So this decision tree model was able to do very well.
All right, we trained our model. It turned out we got pretty good performance with this decision tree model. We found out that the size of the rotor was important in predicting how much energy these wind turbines generated, and that also the year that it was commissioned had a big impact as well. I was really excited to get to make some of those visualizations talking about the variable importance and understanding why the decision tree made the predictions it did, which really highlights why you might choose the decision tree, and also we walk through how to tune it. So I hope this was helpful, and I'll see you next time.